All right. Hello everyone. Welcome to my defense presentation, and it's on solenoids of split sequences. Here's a brief overview of what's in the talk. We're going to start with history and motivation, and then go into introducing our object of interest, which are solenoids, and then we are going to directly go into our results. So among the 5 results listed over there, the first 2 are about the topology of the solenoid, and the last 3 are about the dynamics of solenoids. Specifically, this theorem 1, I consider this to be the main result, and it gives us a mechanism and some tools that we can use to study spaces of transverse meshes of solenoids. And then after we have that theorem, we have this immediate corollary that falls off of that tells us that the space of transverse meshes of a solenoid is actually a finite dimensional cone. And then another application of that is this theorem 2, where we give a criterion for unique ergodicity for solenoids. Now, to prove that, we have to do some little more work. It's not a very direct consequence. All right, and then we talk about further directions and speculations. That's the overview. Okay, so we start with the basic fundamental concepts we study in solenoids, which are minimality and unique ergodicity. Now, think about a specific dynamical system. You can think about a space and a function on it that we can iterate, or you can think about a compact surface with a foliation on it. And in this context, we call this system minimal if each f-orbit or each leaf of the foliation is dense in that space. And we call the system uniquely ergodic if there exists a unique f-invariant or transverse measure up to scaling on Y. Now, both of these concepts are kinds of minimality. One is topological, the other is measure theoretic. And with this backdrop, we can talk about history and motivation. There's a particular broad question that we are trying to contribute towards, which asks this: given a class of dynamical systems, we want to recognize when a system is minimal and when a system is uniquely ergodic. And then we want to know how do these two concepts interact. Specifically, are there examples of minimal yet non-uniquely ergodic systems, and are almost all minimal systems uniquely ergodic? And in the past, this kind of perspective has been used to study dynamics of groups. Digging a little more into those two questions that we posed and some more specific inspirations, there are 2 settings that we are interested in where these 2 questions have been answered positively. One is the interval exchange transformation context, and specifically the work that Veach did in this context. We are going to directly apply some of Veach's results. And then when we try to construct transverse meshes or a notion of transverse meshes on solenoids, we are going to seek inspiration from the measured foliation context. Now, our results that we are going to talk about today are trying to make some partial contribution towards this second question. All right, so now we are going to talk about our object of interest, which are solenoids of split sequences. Now, these are generalizations of toral solenoids that have been existed for a while now. Toral solenoids are inverse limit sequences of circles, and the level objects there are just circles, and in between maps are wraparound maps. And solenoids of split sequences, instead of circles, we are going to use finite cographs, and instead of wraparound maps, we are going to use fold maps. And we also impose the condition that each fold composition has no backtracking. We are going to talk a little bit about what all that means. Now, cographs are graphs with no valence 1 vertices, and no backtracking means that the fold composition restricted to edge interiors, their local homeomorphism, nothing turns back in place. And a strongly, so those are the two things that I needed to explain. And we also have an additional hypothesis that we like to impose going forward, which is called strong properness. Now, strong properness means, in addition to, well, I need to tell you what these folds actually are, so let me backtrack and tell you that. These fold maps are just elementary folds. They are just identifying some two initial edge segments with each other, and these edge segments have the same initial vertex, but they must have two distinct terminal vertices. Because when that happens, we are ensuring that these folds are also homotopy equivalences. All right, so that's for general split sequences. But if we are imposing strong properness, that means in addition to all of that, these folds must also be graph maps. So vertices can only map to vertices. Now, in our thesis, in my thesis, I do go over a looser condition, a looser hypothesis called properness in the initial chunk. But for convenience, we are just sticking to one hypothesis here. This is a stronger hypothesis than the one I generally use. Okay. All right, we are going to talk a little bit about the topology of the solenoid. Now, let zeta be that top sequence, and let it be a strongly proper split sequence, and let x or x of zeta be the solenoid induced by zeta. And going forward, we are going to keep that notation around, and every time I mention zeta, I want you to think of that entire sequence with those notations. All right, and this solenoid lives inside this big product space. And because it lives inside that product space, it inherits that topology. So we are going to construct this a convenient subbasis for the solenoid so we can visualize its topology. To do that, we are going to specify a particular convenient subbasis for each graph, which are just star neighborhoods. And you can see a 4-pronged star neighborhood here and a 2-pronged star neighborhood there. And then a typical element of the standard subbasis is a projection pre-image of a standard star neighborhood inside a graph. I'm skipping over what standard means. If it is needed, I'll come back to that. Okay. So now we are trying to introduce an atlas, a foliated atlas for the solenoid. In order to do that, we are going to talk about the particular cover associated with that atlas. A typical element of that cover is either called a tunnel set or a star tunnel set. Now, a tunnel set is a product between an open interval and a totally disconnected set, and that totally disconnected set is usually Cantor set shaped. So you have an interval crossed with a Cantor set. And in it, this is just going to be a bunch of open intervals stacked on top of each other where cross sections are Cantor set shaped. So this is our typical non-singular neighborhood. And then we have star tunnel sets, which are constructed by gluing together finitely many tunnel sets. So you take finitely many tunnel sets, specify a special path component in each tunnel, and then glue together those special path components in such a way that in the resulting space, in the resulting quotient space, all but one path component are interval shaped, and that one unique path component that is not interval shaped is going to be a star set. So that's a typical neighborhood of our cover that we are going to use. And then we have our first result that says the solenoid has a singular foliated atlas. We are going to just talk about the cover here. As I said, each element of this cover is either a tunnel set or a star tunnel set, and each pair of elements, if they intersect at finitely many disjoint tunnels as well. So this is a very nice cover. Now there I'm saying we have a finite cover, we do have a finite cover, but we also have a much nicer version of this, which is an infinite cover, but it's a much finer cover. And that much finer cover is also nice because it generates the topology of the solenoid. So we are going to use one or the other cover as necessary. Now, one more piece of terminology that I need to define is that in the solenoid we have two types of points. One is called a leaf interior point, the other is singularity. A leaf interior point is a point that is contained in a path component of a tunnel, and if it is not that, it is called a singularity. And we are going to use this foliated structure to study dynamics of the solenoid. All right. So, speaking about dynamics, we have to talk about transverse meshes, and we are going to build up to that. So, to investigate, our main inspiration is the surface case, and in the surface case, in singular foliated surfaces, specifically transversals are defined as these open arc segments that are transverse to the foliation leaves. But in solenoids, we don't have a differentiable structure to give us transversality. So instead, what we do is we use that local product structure that we established. The nice thing about that is that our solenoid has only finitely many singularities, and when we remove those, the non-singular portion of the solenoid is entirely covered by these nice tunnels called turn tunnels. Now, these are our main tool in studying that non-singular portion, so I'm going to sort of have this terminology zoo a little bit later, but before that I'm going to talk about turn tunnels specifically. Now, to do that, I need to first tell you what a turn is. Now, a standard turn is an embedded interval in a level graph that contains at most one natural vertex, and then every open interval shaped thing in the solenoid that projects to that turn is called a leaf segment that takes that turn. And we collect all of those leaf segments for a given turn. We collect all of those leaf segments that takes that specific turn and take the union, that is called the turn tunnel of that underlying turn. That's what a turn tunnel is. And then once we have that, again this is a tunnel, so you have this nice product structure where path components are leaf segments, interval shaped, and you have these cross sections that are cantor-set shaped, and any cross section of a turn tunnel is called a turn transversal. All right. So now we have our specific terminology that I need to clarify. This will be important later. So when you have a turn tunnel, when you have a standard turn in a level graph, if that turn is contained in an edge interior, then we call it an edge turn. If not, we call it an exceptional turn. And we also define tunnels and we also define the turn tunnels in that same style. We have edge tunnels and exceptional tunnels, edge transversals and exceptional transversals. And later we will use these exceptional transversals in a particular proof, and that's going to be important later. Okay. All right, so we have defined these cross-section transversals that are basically straight transversals, but we have to define transversals in general. Now, to do that, we have to first define these things called flow maps. A flow map of a turn tunnel is a homeomorphism that continuously deforms a cross-section along leaf segments, and a transversal is an image of any Borel subset of a turn transversal under a flow map. So you can take an entire straight cross-section and deform it and call it a transversal. You can also take a Borel subset of that cross-section and deform it, and that is also a transversal. Now, true transversals are called flow equivalent to each other if there exists a flow map composition taking one to the other. All right, this is specific definitions if anybody needs, but I am going to now read out this specific definition of transverse meshes. So we talked about what flow equivalence is. A transverse measure, and bear with me now because I'm ignoring this adjective over here that says non-atomic, but I mean it, it's there. So let me just say that. Okay, a non-atomic transverse measure on X, X being our underlying solenoid, is a non-negative function on the set of all transversals such that it satisfies those two conditions. The conditions are, for each transversal, this mu restricted to the Borel sigma algebra of the transversal is a non-negative finite Borel measure on the transversal. And the second one is, if you have two transversals that are flow equivalent to each other, then the measures must be preserved by any flow map composition. So again, on the restriction to this non-atomic cases, now transverse measures are not generally non-atomic. They can absolutely possess atomic masses. But to possess an atomic mass, a solenoid must have at least one finite leaf. And if it has a finite leaf, that means that solenoid is non-minimal. And at the moment, we are not interested in the non-minimal case. So we are going to restrict our context a little bit more into these things called expanding solenoids, which do not contain finite leaves. Every leaf is infinite and therefore do not carry atomic masses. So for this purpose, as long as we stick to expanding solenoids, this definition is fine for transverse measures. Okay, now this is a good time to talk about minimality. But we can't talk about minimality without talking about leaves. Now I already told you about transversals. They live inside this non-singular portion of the solenoid. And inside the non-singular portion, because there are no singularities, we are going to sometimes focus our attention into that non-singular portion when talking about minimality and leaves. So we are going to talk about leaves that are path components of the solenoid, and we are going to talk about partial leaves that are path components of the non-singular portion of the solenoid. And these leaves are going to be immersed grafts in the solenoid, and these partial leaves are going to be immersed one manifolds in the solenoid. Now, on to our second result, which is giving a combinatorial criterion on how to recognize minimal solenoids. Now, again, the baseline hypothesis is a strongly proper split sequence. And then we say that the solenoid is minimal if each partial leaf is dense in the solenoid. Now, our mingling lemma says that if the split sequence is fully mingling, then the given solenoid, induced solenoid is going to be minimal. But what does full mingling mean? All right, I'll tell you. Let's look at our split sequence. It has these fold compositions. We say that a fold composition is fully mingling if each natural edge in the domain graph goes over the entire range graph. So each edge in the domain interacts in some way with each edge in the range. That's what a full mingling fold composition is. And in this sequence, if we have infinitely many full mingling fold compositions appearing, then we say that the sequence is full mingling. And then you have the mingling lemma. But why do we care about this lemma? Well, for one, very little is needed for the converse to be true as well. So it's a very strong criteria in that sense. So that's nice. But primarily we care about this direction because full mingling will function as a prerequisite for our uniquely ergodic criteria. When we define our uniquely ergodic criteria, that's going to be semi-normality. If a solenoid satisfies semi-normality, it will be true by default that it also satisfies full mingling. Therefore, that solenoid will be minimal as well on top of unique ergodicity. So that will be nice. All right, so next up, we are going to talk about dynamics of solenoids. Okay, on to our main theorems. So again, the hypothesis here is that X is strongly proper and expanding solenoid, and TMX denotes the space of transverse measures of X. Now, our theorem 1 is giving a mechanism of how to envision the space of transverse measures. It basically tells us that the space of transverse measures of X is the inverse limit of a specific sequence of cones where the in-between maps are linear maps. Now, I'll tell you in a minute what these cones are and what these linear maps are exactly, but right now I want to talk about the applications of Theorem 1. So, the first one is a very direct cone sequence. These cones in the sequence are going to be finite dimensional cones, and therefore, when the underlying split sequence is of rank n, we have this particular bound on the dimension of Tmx. And that bound only depends on the Euler characteristic of the graph, or the rank of the graph. Both are linear on each other. And then our second application is Theorem 2, which takes a little more work to prove. And basically, it's just what I said before. If we have a seminormal solenoid, then that solenoid is uniquely ergodic, i.e. Tmx is one-dimensional. And we'll use this cone sequence to prove that result as well. Okay, I promised to tell you about these cones and these linear maps, so let me do that. All right, so we have our split sequence given to us. We are going to construct this cone sequence, and there's a bridging concept which is basically a sequence of vector spaces. For each level graph in here, for each G sub j, we are going to define the real vector space spanned by the set of natural edges of Gj. So that we are going to call Rj, and then in between these Rj, when you envision this Rj sequence, the in-between maps are going to be linear maps. So from Rj to Rj plus 1, we can define a linear map. It's going to be the linear map defined by the transition matrix of the corresponding fold f sub j. And then we are going to look at each of these Rj's, each of these vector spaces, and we are going to pick the cone of non-negative vectors inside of them, and that's what we called lambda j. And when you look at this lambda j sequence, the in-between maps are going to be the restrictions of those linear maps. I know this should say restriction. I didn't want to mess up the notation, so it says just Tj, but Tj is a map on Rj. This here is supposed to represent the restriction to the cone. Now, these cones are called pseudo-weight cone sequences of zeta, this lambda sequence that is. All right, so the inverse limit of this lambda sequence, we call it lambda or lambda of zeta sometimes when we want to specify the split sequence. And our claim is that that lambda is actually equal to Tmx. Now, this is the premise of our proof. Each element of this lambda, this inverse limit, we call each element of lambda a weight assignment on zeta, and each transverse measure, well, then what we have to, Then what we have to show is that each transverse measure induces a unique weight assignment and vice versa. Now, the first direction is much easier than the second, so we are going to do that one first. Okay. So we have to prove the direction. Each transverse measure induces a weight assignment. All right. The bridging concept for this is going to be called edge weights. Now, given a transverse measure mu on X and an edge, a particular edge in a level graph, now this is going to give us an edge tunnel, and that edge tunnel is going to have a bunch of edge transversals that mu is going to give a total weight to. And each one of these edge transversals that corresponds to the same edge is going to have the same total weight with respect to mu. We are going to take that number and we are going to call that the edge weight of E, and we are going to denote it by mu of E. All right, so given a transverse measure mu, each edge has an edge weight. All right, so now we have to construct a weight assignment, a W, out of that. But what is a W? Well, we have our split sequence here, our sequence of vector spaces here that are spanned by edge spaces, and then we have our lambda sequence. a W that lives inside this inverse limit lambda can be represented as an infinite tuple of Wj's. Each Wj lives inside the corresponding lambda j. And each one of these Wj's, let's just focus on W0 for a moment. This W0 is a vector that lives inside lambda 0, and we can unravel that as well. It's going to be a finite tuple, and each component in this tuple is indexed by an edge that lives in G0, a natural edge in G0. So for each natural edge in G0, we have a component here. So that's exactly how we define the weight assignment induced by our given transverse measure. We just take each edge weight given by mu and assign it to the corresponding component of Wj. And we get a weight assignment that makes sense, that satisfies the necessary linear map acting on them. So that's the first direction. That was very straightforward. Now to the second direction. The second direction tells us that lambda zeta, any weight assignment defines a unique transverse measure. So now we have limited information to construct a more elaborate object. Now this follows from the two lemmas that are listed over there. Lemma 1 basically implies lemma 2, and then lemma 2 implies everything else. So lemma 1 tells us that each turn tunnel, turn I of X, can be written as a disjoint countable union of edge tunnels and a bunch of finitely many extra leaf segments. Now, talking about those leaf segments that live inside turn I, now there are two types of leaf segments that live inside a turn tunnel. One type is an edge leaf segment. An edge leaf segment is a leaf segment that projects to some edge interior in some level. That's an edge leaf segment. And the other kind is called a pseudo-singular segment. A pseudo-singular segment is a leaf segment whose projection at each level contains a natural vertex. So, the sequence of natural vertices, one from each level graph, that corresponds to a particular point in the solenoid. If we take a point in the solenoid, and if that point at each level projects to a natural vertex, we call that point a pre-singularity. It doesn't always have to be a pre-singularity. Sometimes we have these pseudo-singularities that pretends to be singularities, but they're not. So, but these pre-singularities project to natural vertices at each level. We can show that the number of these pre-singularities is actually finite. So therefore, we can only have finitely many pseudo-singular segments in a given turn tunnel. So now we have these finitely many leaf segments put aside, and then we have the collection of all of the edge leaf segments. So what we need to show is that the union of all edge leaf segments in turn I can be represented as a countable disjoint union of edge tunnels. So we put that proof over here, but let's suppose that is proven, right? If lemma 1 is proven, then lemma 2 says each turn transversal edge can be written as the disjoint countable union of edge transversals and a finite set. So turn transversals are cross sections of turn tunnels, so that is a direct consequence. And if we can do that, well, we have already specified a weight assignment. Then that weight assignment defines an edge weight on each edge transversal. And then we have our big turn transversal, and we'll have a countable disjoint union of edge transversals inside it and a finite set. We are in non-atomic measure territory. We can disregard finite set. We can add up all the total measures of these edge transversals, and that will give us the total measure of the turn transversal. So that gives us enough information to construct this transverse measure. So that will be our proof as long as lemma 1 is proven. The meat here lies in the proof of lemma 1. So let's prove lemma 1. Okay. Now lemma 1, again we have a given turn tunnel, and let's say the turn corresponding to it is I, and I'm just assuming this I lives inside level 0 for convenience, but it could live inside any level and the proof will be the same. So we have a turn tunnel, we have the turn I corresponding to it. We have to show that this is the disjoint this is a disjoint countable union of edge tunnels and finitely many leaf segments. Alright, so what we are going to do here is we are going to take our specific turn that we have, and in the previous level we can mark all the turns that map to that given turn. So we can have up to 2 turns in the previous level that maps to this turn, and we can keep doing that at each level, and that gives us this tree structure. We call this the tree of preturns. Alright, so we look at this tree, and then some of these nodes are going to represent edge turns, some of these turns are going to represent not edge turns. And whenever it represents an edge turn, we color it yellow and we color everything below it in red. So we do that from top to bottom. We go from top to bottom and mark off the first edge turns we encounter in yellow and mark off everything below it in red. Then all of these yellow dots are going to correspond to some maximal edge turn or a maximal edge tunnel inside the given turn tunnel. So if we just collected those maximal edge turn tunnels or maximal edge tunnels and take their disjoint unions, because they are going to be disjoint because they're maximal, everything left over in turn tunnel that's not in there are going to be those pseudo-singular segments, and they're just finitely many. So we are done. That's the proof. Okay, that's the proof of theorem 1. And now on to theorem 2. This claims that semi-normal solenoids are uniquely ergodic. Alright, so before we move on to the proof, I have to tell you what semi-normality means. Alright, so let X be a strongly proper expanding solenoid. Then we say that a matrix M is realized in zeta if M is the transition matrix of some fold composition that appears in zeta. And we say that that matrix M is, we say that a matrix M that is realized in zeta is recurrent in zeta if it corresponds to infinitely many fold compositions as its transition matrix. So it has to appear separately. A fold composition here and a fold composition here and a fold composition here, each fold composition corresponding to the same matrix. If that happens, we call it recurrent in zeta. Alright, we say that X of zeta is a semi-normal solenoid and the split sequence is semi-normal if there exists a positive square matrix that is recurrent in zeta. Alright, so now we want to show that when zeta is semi-normal, TMX is one-dimensional. And the main tool we use here is a lemma by Veitch. So first, let's understand that lemma. Alright. Now the setting of this lemma, so once again it's using a sequence of cones and we have these restrictions of linear maps in between them. Now Veitch uses these linear maps that Veitch uses, they are injective. Now for the proof of this lemma, it doesn't matter that they're injective, but they are injective nonetheless in his setting. And each of these cones are of the same dimension. And also all of the matrices corresponding to these linear maps, they are at the very least non-negative and not all zero, no zero matrices appearing here. So those are the hypotheses. And then additional hypothesis for the lemma are that this cone sequence take the format of, well, he has one positive recurrent matrix that he calls B, and everything that is not that B, that is the in-between matrix, is going to be non-negative and not all zero. And if all that is true, he goes to the 0th level cone and he constructs this guy inside of that cone he calls lambda. Now what is lambda? Lambda inside the 0th cone is the intersection of all the images of previous cones inside of it. You take this guy, take its image inside of the 0th cone, you take the negative second cone and take that guy's image inside the level 0 cone, and keep doing that and take the intersection and you get omega. Alright, so once he gets omega, his lemma gives us that omega is going to be one dimensional as long as we can find one recurrent positive matrix. It's a very nice lemma. Alright, so we want to apply this, but we have some concerns. Okay. A, our cones are not of constant dimension. Well, that's not too bad because we have, we have to have at least some recurring dimensions in our sequence because our involved graphs have the same rank. So that's not too bad. We can just find a recurrent dimension, especially if we are supposing semi-normality that suggests that we have some recurrent dimension. So we can take that sequence, we can just focus on those levels and compose everything in between. So that's not a problem. The other thing is our linear maps aren't necessarily injective. Okay, well, now Veach is in a setting where his maps are injective, but for this lemma, he's actually not using the fact that they're injective. So in our sequence, our omega equivalence would still be one-dimensional. But here's the kicker. Now, the way Veach applies this cone sequence is to go, all right, he's interested in figuring out something about a space of invariant measures. And his invariant measures is the inverse limit of the sequence depicted in this slide. Now, all he wants to show is that that inverse limit is one-dimensional. What he showed is that omega is one-dimensional. But omega is the projection at level 0 of that inverse limit object. It always is that. But in his case, because these maps are injective, that inverse limit's projection to level 0 is going to be injective as well. So if omega is one-dimensional, so is the inverse limit. So he gets that his space, his invariant measures are just like one measure up to scaling because his space of invariant measures is one-dimensional. So that was his context. But in our context, we don't have this injectivity, so how do we handle that? All right, so here's the rest of the proof. Now, as I said, we begin with, so first supposition is that we have semi-normality because what we need to prove is that if we have a semi-normal sequence, then it induces a uniquely ergodic solenoid. So we assume semi-normality, which means we do have a square positive matrix recurring. So we take that square matrix, let it be D by D matrix, right? So that means we can go to all the levels where this matrix's linear map starts and ends, and we can just focus on these levels because then we can have, all right, this matrix, this linear map is going to recur in this condensed sequence, and then we can compose all the in-between maps as well, at beginning with the end of that recurring linear map and ending with the beginning of the next recurrent linear map, and then compose that. So focusing on that, those specific levels where these matrices linear map begins and ends, we get this condensed version of the lambda sequence and condensed version of everything we can write in terms of those levels. All right, so we do that. Now what? Okay, so we just dealt with that 1 omega inside the zeroth cone, but it is also true because we have this recurring matrix or recurring linear map. Every time we have a level where this recurring linear map, where the specific level cone is the range of that recurring linear map, we can specify that level and define an omega. In fact, we can define omega for each level, but those are the ones that we are going to use. All right, so for each level j, omega j is just, again, it's the same principle. It's the intersection of all of the imagers of previous cones inside this particular level cone. That intersection is omega. Now, once again, inverse limit object of this omega sequence. Now, we have the same linear maps as in between maps, the restrictions of the same linear maps. We take the inverse limit of the omega sequence, and that inverse limit is still going to be equal to lambda and tmx. And that inverse limit, which is equal to tmx, is still going to project to omega onto omega at each level. That is also true. It's not going to be an injective projection, but we are going to have this. We are going to have an infinite sequence of levels where these omegas would be one-dimensional, because we can we can pick a level where that level cone is the range of that recurring linear map, and we can just start the sequence there. It's going to have the same inverse limit, and that initial chunk chopped off sequence is still going to follow the Veitch style. So Veitch lemma is still applicable there, and that's going to show that the corresponding omega is one-dimensional. So there we have an infinite sequence of omegas that are one-dimensional. Well, the dimension of the inverse limit is bounded above by the lowest recurring dimension of these omegas. So we are done. That means tmx will have to be one-dimensional. So there we go, the end. I think I finished early. I do have an epilogue, but should I ask if anybody has questions now, or should I just go through the epilogue?
Yeah, let's have questions.
Let's have questions, okay, cool.
Should we clap first?
Let's clap.
Also, thank you for listening. What do I do?
Question, Ilya?
Yes, actually, I had a question.
Yes.
This theorem about unique ergodicity, as I recall, you also proved something about finite dimensionality, right? So.
Yes, sorry, I skipped over that.
Can you hear what I'm saying?
Yes, I can. Can you hear me?
Yes. Yeah.
Okay.
So, what do you prove about finite dimensionality of this TMX?
Finite dimensional. Okay, let me
Is
go
it
back.
always sometimes finite dimensional? Do you actually get a bounded dimension?
Yes.
And when? Can you say something about this?
Yes. Let me go back. Right, that's where I had the bound. Okay, so remember that sequence of lambdas that live inside sequence of R's. And those R's are actually the vectors at each level j. It was the real vector space spanned by the set of natural edges at that level. So the dimension of these Rj's are bounded above by the number of maximum natural edges attainable for graphs of that rank. So that bound comes from, well, we have a constant rank for our graphs because they have the same Euler characteristic. So the dimensions of Rj's themselves are bounded above by that exact number, 3 times n minus 1, n being the rank of the graph.
So this is a really general result, I see. Okay, very good.
Okay. Yes.
I wondered, would it be possible to improve that like by 1? Like,
Yes.
down to
It is.
3
It
minus
is.
4?
It is.
Okay, cool.
Because like one has to.
Yeah,
we are
yeah.
dealing with false. One has to split away. Yeah, I
Yeah.
didn't want to.
Cool.
Yes. Yes.
Is there any intuition you can provide for what the semi-normality condition is doing, like, topologically or otherwise? Like, I couldn't really get the sense of that.
So what it ensures, in my mind. So let's say this is the vector space Rj, and then let's just take the same R to the power 3 or something, some vector space, right? And then we have the non-negative cone, and we have a positive matrix acting on it, and it's going to obviously contract the image cone, and this contraction keeps happening, but what's important here is that keeps happening in such a way that the remaining thing becomes only this array. That actually comes, well...
Can we go to the slide where that's defined?
Oh, sure.
Just because I don't have it holding in my head.
Okay. Not filming.
I think it was maybe later.
Yes. Wait, am I going back?
Yeah, you are.
No, wait, did I go past it? No.
I think I saw it pop up.
Oh, yes. There we go.
Okay, cool.
Yeah, it just means we have a sequence of maybe. So we are discussing this for sequence of split. We're discussing it for split sequences. We call the semi-normal. A split sequence is semi-normal if blah 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 is true. But basically, what it implies is that if you go to the lambda sequence or if you go to the R sequence, the in-between linear maps, you can compose them, and then this gives us a linear map. And if one of those composition linear maps is recurring and corresponds to a positive matrix, and it's square, then yes, it's
So
called
like,
semi-normal.
if my fold maps were like, I have some nice train track map or something, and I'm just like doing that like constantly, that would be a good example?
That would be it. Yeah,
Okay.
yeah. So they are always, if you're iterating a train track map, that's going to be a periodic sequence.
Yeah.
So these kinds of results for periodic sequences are known. Like there's even a better bound on the dimensionality of TMX in that setting. So what's interesting, or what I found interesting about this one, is because these sequences don't have to be periodic. So our goal was again trying to answer that second question of like, is this criteria, is unique ergodicity generic in the setting of the space of solenoids? And if you're only looking at periodic sequences, well, that's not going to happen if that's the only setting you work on. But this guy, semi-normal criteria, this has a very good chance of being generic. That's the kind of the motivating factor here. Sorry, I didn't think I answered you.
That's helpful. So I think I guess maybe it's just that I'm not pushing it, but like to me intuitively that seemed not very generic. Like I must be misunderstanding something. I mean, because can't you like perturb these sequences a little bit, and like if I now like I need to recur like on the nose, right? Exactly.
I think you're like flipping a for all to a there, and there exists, or vice versa. Like we just need one recurrent sequence, not that every finite sequence recurs.
But,
It's semi-normality, not normality. Like not. So so this is kind of why I added semi. I don't know if that is what you're asking about, but there is this criteria that says if you have a sequence, then any finite composition that appears should appear infinitely often. This is not that. This is just one finite composition that is positive recurs. That's all. And because of if this square requirement is throwing you, that's fair. That was something that Lee also had back in the day. That can be overcome, I believe. Yes.
Quick question. Is it true that more than one inverse limit could represent the same solenoid? So for example, you could have one inverse
depends
limit
on what you...
not have one of these recurrent,
Oh.
have the recurrent property, and then one that does. So this property, while it might not seem standard, actually might be standard because you can find a nice inverse limit for your solenoid.
That depends on what you call same. If what you call same is there is a homeomorphism and there is an equivalence relationship between each level graph in such a way that each pair of level graphs in the two sequences have homeomorphisms, that's a very strong sameness. In that case, if one is semi-normal, I think the other has to be semi-normal. But if you are like joining these two sequences with like homotopy equivalences, then this might be maybe true. I'm not sure. I'll have to think about that. I still think yeah, I'm just gonna say it's gonna depend on the sameness, and the looser you make your sameness criteria, I don't know, maybe there's a way of extracting still some dynamical information about that other sequence by working on the nicer sequence, but maybe, I don't know.
Other questions?
Can you say a little bit more about why the lowest recurring dimension is an upper bound on, like, you know, you have your omega ki's that are all one-dimensional. Like, I'm sure it's just a quick thing, but like, why is that an upper bound on the dimension of PMX?
So, I guess. I don't know if the people on Zoom can see the board, but I'm just gonna write here. Okay, so we have omega, so we have lambdas. And we have omegas. So the inverse limit here is equal to the inverse limit here, even though these guys are just inclusions. Right. So let's say this omega bar has a so this has a vector space structure coming from the vector structure of that R tilde, and then the guys that live here are just vectors. So if you have a pair of vectors that are linearly independent, let's say the lowest recurring dimension here is D, and if we have a D plus 1 set where each pair is linearly independent, then you have to be able to project somewhere down the line. There must be a projection where these are distinct or linearly
but then you
independent.
can, like, it's coming from a one-dimensional thing. So okay, cool, thank you. Yeah.
Okay.
So can I ask a follow-up question? Okay, so I think that I misunderstood what transition matrices, how much they were evolving, but just to understand. So in a sense, like a transition matrix, it's kind of locally constant in the sense that if I am like perturbing my fold maps, like it's like counting.
It's counting how many times an edge goes over another edge.
Got it. Okay. Okay. So it's like pretty stable at first. Okay. Okay. Got it. I see.
Well, if that's all, we have to meet the members of the committee. And perhaps you could start a new Zoom session unrecorded for us to meet?
Oh, I'm
Could-
not recording the Zoom
Oh.
session. He's just recording the
Oh, with the camera.
camera. Yeah.
Oh, okay.
So he can turn that off
Then perhaps you can turn the camera off.
and, and kick Alex off. Oh, okay, Alex already. He's already gone.
Bye, Alex. Thank you. You're gone.
So what do we do?
Okay.
Well, we have to decide whether she passes.
Yes. Okay.